Let's take a moment to review the properties of a gas. Right now, these particles of gas are diffusing or spreading out into this space, and they're moving at an average kinetic energy of some amount, which means they have a certain temperature. Increasing the temperature increases the pressure, so that's a relationship between temperature and pressure. That means that the particles have a higher average kinetic energy or higher temperature. If I cool them down, then the particles are going to slow down, the temperature is going to decrease, and the pressure decreases as well. So right now we have a pressure sitting around the 40-41 atmospheres mark. If I were to cut the volume in half, notice that the pressure basically doubles. So now we have the relationship between pressure and volume as well. But in addition to pressure, volume, and temperature being variables that can describe the system of gas, we also have density. We're going to derive the gas density equation because I think it's interesting, but it also helps you understand the factors that influence the density of a gas. To understand it, you must recall the regular density equation, D equals m over V. Sometimes you'll see rho instead of D, the Greek letter. It just means density. We're going to stick with D here. And you should also know the ideal gas law, PV equals nRT. Let's see how they can be combined to give us a single equation for the density of a gas at various pressure, volume, and temperature conditions. To do that, we'll take the first equation and we will rearrange it, and we'll get V is equal to m over D. So we solved for V. Since volume is equal to mass over density, we can replace V and the ideal gas law with m over D. Now I'm going to rewrite this by just putting the P and the m in the numerator position and D in the denominator. So we have P times m over D is equal to nRT. I'm going to take this equation and I'm going to rearrange it to solve just for density. D is equal to P times m divided by n times R times T. And it does help for us to recognize something else. We have an m over an n. If we think back to what we know about molar mass, we know that molar mass is grams over moles. So what variable is used to represent mass? That would be m. And then what variable is used to represent moles? That is n, which means that the molar mass, capital M, molar mass, you might also see it abbreviated as just a sideways capital M, but I'm using double M. Molar mass is equal to m over n, which means we can actually replace m over n with the molar mass variable in the numerator. That gives us that density is equal to pressure times molar mass divided by R times T. So let's tidy this up a bit. After using the density equation and the ideal gas law and then substituting MD, M2 where V is, we get this equation which we rearranged to solve for density, and then we recognize that m over n is really just another way to represent molar mass, so we substitute in molar mass for whatever that particular substance is, and that is how you do it. R is going to have a specific unit, so let's examine what that unit is. R is a constant, and that value is 0.08206, and the units are atmosphere liters per mole Kelvin. And that's going to be helpful for us because we're also going to examine where did 22.4 come from for the density of a gas at STP. Now let's check our units for all of these things. So pressure is going to be atmospheres. That's the unit that is ideal and standard for these type of problems. And then the molar mass, that we already know is grams per mole. And then in the denominator we have R, which we know is atmosphere liters per mole Kelvin. And then T is just Kelvin. So what cancels out and what doesn't cancel out? If we zoom in here, we see that atmospheres will cancel because it's in the numerator of the numerator and the numerator of the denominator. We also see that moles will cancel in the denominator double position, and then Kelvin will cancel again here. That leaves us with these units, grams per liter. So that means that when you are calculating density, the unit that you should ideally get is going to be some number, and it's going to be grams per liter. These are common units for the density of a gas, assuming that all the other units are these, which are pretty standard for gas-related problems in chemistry. So we have our equation for the density of a gas, and this technically works at any temperature and pressure as long as it remains a gas and we pretend like it's acting very closely to what an ideal gas acts like. But we also want to answer the question, what is STP and where did that 22.4 liters per mole number come from that some teachers and professors ask you to memorize when you do gas stoichiometry? That only works, this number 22.4, only works when the gas is under standard temperature and pressure. Standard temperature is considered to be 0 degrees Celsius or 273 Kelvin. Keep that in mind because we're going to plug that in to the density equation for a gas to see where that 22.4 comes from. And then regarding pressure, standard pressure is simply 1 atmosphere. So we have two things to substitute in our equation. We have temperature, which we're going to replace T with 273 Kelvin because that is considered standard temperature. And we are also going to need to replace the P with just 1, which is standard pressure. With our substitutions, we get 1 in place of P, we get the R value, which we just know is a constant, and we put 273 in place of T, where 273 refers to the temperature in Kelvin. And something interesting happens in the denominator. It turns out that the product of R and the temperature in Kelvin is actually just 22.4. And since anything times 1 is itself, we can get rid of that in the numerator position. And this is interesting because it leaves us with two equations, the density of a gas under any conditions and the density of a gas at STP conditions. When do you use each one? You can use the first one anytime, as long as you remember that under standard conditions, P equals 1 and T equals 273. But if you don't have to know that, or if you just have to calculate the relative density of gases and you can just assume they're all at STP, you can use the second one, which is only usable at standard temperature and pressure. This one just kind of neatens and tidies everything up ahead of time. So all you would need to calculate the density of a gas at STP is the molar mass, because the T and the P, the temperature and the pressure, are already understood and accounted for along with R in that 22.4 value. So let's practice. We're using this equation, which is the same as this equation. So you can use either one. I also just happen to write it in the more standard format because rho is sometimes used instead of D, and a script like italic capital M is sometimes used instead of double M for molar mass, but they're literally the same thing. This question says, what's the density of carbon dioxide, CO2, at 25 degrees Celsius, pressurized at 12.5 atm? 25 degrees is not standard temperature, and 12.5 is not standard pressure, so we can't just use molar mass divided by 22.4. We have to use the more expanded density equations for the gas. Carbon dioxide is what is used to give sodas their bubbly nature. That's why it's called a carbonated beverage. So these carbon dioxide canisters are actually pretty common. Some people just prefer to carbonate their own sodas instead of buying them. So to do this question, we would say, well, D is equal to, we know the pressure is 12.5 because it's here, and we know the molar mass of CO2 is easy to calculate. It's C plus O. That's about 44.0 grams per mole. And we would divide that by the value for R, which is 0.0821 or 0.08206 if you want to have a little extra digits. And then, of course, the temperature is not correct. We need to convert the 25 degrees Celsius into the right temperature. So to do that, we're going to do 25 plus 273. And that's because if you have a temperature in Celsius and you add 273, that'll give you the temperature in Kelvin. So that's going to be 298 here. And when you do all your math, you get about 22.5 grams per liter. So that would be the density of carbon dioxide under these conditions. Now let's think about how the density would change under different conditions, because it's important to understand the relationships between these variables and density. If the temperature goes up, you're dividing this by a larger and larger value, and a higher temperature, will result in a lower density. We would say that temperature and density are inversely related. When the temperature goes up, the density goes down. That's why hot air rises. Pressure is directly proportional to density, because if pressure goes up, then density will also go up because the particles are more closely packed together. We also have molar mass in the numerator, which means that molar mass is directly proportional to density as well. Substances with a higher molar mass will have a higher density than substances with a lower molar mass, because again, it's more mass packed into a tighter amount of space.